portion is basically indicating that overlap zone. So now the overlap, there is a significant amount of overlap. That means energy transfer is possible, and the quenching is due to the energy transfer only. So this is a CDT ZNS quantum dot. I represented this quantum dot here, and this is the acceptor molecule, nothing but this is organic dye molecule. And this quantum dot has a oleic acid capping agent at the outer surface that is negatively charged, and rhodamine 6 is positively charged. So obviously they will form complex when I mixed it in water. Okay, so this overlap portion that is shown by this shaded portion, it is denoted by overlap integral. So more the value of overlap integral, more will be the energy transfer efficient. So here the value is 4.5 into 10 to the power 15. That is is indicating significant amount of overlapping. So now I synthesize this quantum dot, followed by the sum of this quantum dot through TEM, and I found that the size of quantum dot is around 4.5 nanometer. Okay, and this is showing rotational anisotropy decay. What is rotational anisotropy decay? So this is representing how fast this is my model, how fast it is rotating. Now here this curve is signifying that is within 230 picosecond, and here rotation is very slow. So this is showing the rotation of the complex, that is rhodamine 6 along with quantum dot, and here it is showing the rotation of only rhodamine 6G. Now when there is only rhodamine 6G, there is no quantum dot, I can find the rotation is very fast, because obviously this rhodamine 6G molecule is very small. Hello, am I audible now?
Sir, your presentation mode has gone off. You have to turn it off once.
I know. It was disconnected for some.
Actually, sir, because of some unintentional interruptions, if someone opens the presentation mode, your mode will go off. That's the problem.
Okay, Abhijit, is it visible now?
Yeah, sir. It's coming. It's coming. You have to open the presentation.
I have to open the presentation. Okay. Now it is visible completely.
Yeah. You can go in full screen mode. Yeah.
Sorry for the interruption. It's happening again and again. Okay. So it shows that the rotational anisotropy becomes slower when this rhodamine 6G gets attached. It's attached with the quantum dot, because the size when rhodamine 6 is attached to the quantum dot, the size is much bulkier, and obviously you are no longer presenting. Same problem.
The problem is some people actually, when they are entering, they have started presenting. Mr. Gopalpal, please, I request you to stop your presentation mode. Please, kindly don't interrupt the speakers in between. I've already told, I'm repeating once again to the audience, please don't start your presentation mode and don't disturb the speakers. It's a request. Sir, you can start it. Sorry for the interruption.
Okay, no problem. So is everything is fine now?
Yeah, but you have to start the presentation.
Okay, can you see my screen? Is my screen?
No, sir. You have to start the presentation mode. You have to start. The mode is not on.
Start again. I understand.
That's the problem, sir. Every time someone comes in, your mode will go off. You have to manually start it again.
Okay, now it is fine.
It's coming, sir.
It's coming.
Yeah, now you can open the presentation, sir.
It's already open. Can you see it?
Yeah, it's coming, sir. Please continue.
Okay. So when this rhodamine 6 is complex with quantum dot, now the size is bulkier, so you can see the rotational anisotropy time gets longer. So this observation indicating that there is a complex formation between these two molecules, and this complex formation will lead to the threat. So this is showing the quenching of donor emission after addition of protein. We find the emission of the donor is decreasing at the cost of increasing the emission of the molecule, that is the signature of threat. Now, when I normalize the area under curve, it shows there have been an isoemissive point between the emission peak of donor and acceptor. This isoemissive point indicating that donor emission is up. So that this is indicating that if X amount of emission is going from the donor side, the same amount of emission will be received in the acceptor end. And that is the reason behind arising the isoemissive point. This isoemissive point is very interesting here and indicating this is a threat. And now if we look into fluorescence lifetime profile, we measure in TCSPC, we found that donor emission is quenched at the cost of rising is coming in the acceptor's emission. This rising indicating again the threat is taking place. So now next we did time resolved emission spectra in steady state emission spectra, that is a equilibrium process. But now we see the emission process or emission spectra at different time. So that is possible in a CSPC instrument, and with some post treatment of the lifetime profile, we can able to generate the emission spectra of the molecule at different times. So now I basically plotted the emission spectra of donor acceptor pair at different times, starting from 0.1 nanosecond to 1 nanosecond. So this is the rhodamin 6G portion, and this is the quantum dot. These two peaks are very closely spaced, and it is very difficult to separate these two peaks. That's why the threat study in this system is very challenging. Now we found that as time progresses, this portion emission intensity of the gut, at the same time the emission intensity of rhodamin 6G portion increases. And again we found, like steady state in time resolved study also, there have been a isoemissive point, and this is indicating this the threat is going up. Now the question is, since these two peaks absorb emission, low emission of acceptor is so closely spaced, how one would study the quenching process? So when the donor peak of the acceptor emission interfere that and further. So what we did, we basically splitted this individual spectra using a binomial curve. And where in binomial thing, we fixed the peak position corresponding to 16 and another quantum dot, and then we splitted it one spectrum to two spectra, and in two individual window, we basically plotted all the spectra as a function of time. And this portion corresponding to the quantum dot portion, and this is corresponding to the rhodamin 6G portion. You will find as time progresses, the emission intensity decreases. Here it is increasing. Now if I plot area under curve as a function of time, we'll get this kind of decay curve for quantum dot and a rise curve for rhodamin 6G. Why rise? Because the intensity of rhodamin 6G increases. Now that as we increase the concentration of rhodamin 6G, or if we decrease the C of quantum rhodamin 6G, your threat time scale will be faster. This is obvious because when you have large number of acceptor around the donor, then it will be more efficient. We found this different ratio of quantum dot is to rhodamin 6G or threat time scale. This is 5 to 2.2. And when it is 1:2, your time scale is become shortened. And so the next steps to finding the donor acceptor distance, because we know FRET is used as a molecular ruler. So obviously it is a common interest to measure the donor to acceptor distance from the FRET time scale. And using this equation, this is the case that rate we can get it from quenching ratio, and tau rate is the time scale, the time scale, and R0 is the Foster distance calculated theoretically using this equation, and RDA is the donor to acceptor distance, that is our interference, and we measure this one, and tau 0 is basically lifetime of donor in the absence of acceptor. And we found from this time component is corresponding to a distance 3.8 nanoseconds, 3.7, 0.4 nanosecond. But the thing is that from the table we found the this core of this quantum dot without this capping layer, that is around little more than 5 nanometers. So the radius is around 2.3 nanometer. And we found from DFT calculation that size of a rhodamin 6 is a radius around 0.7 nanometer. So now if I add 0.7 and 2.3, so it is not, it is coming something not equal to 3.8. So we are assuming that this molecule is basically embedded deep inside this capping layer. So this is not neither in the interface nor in the very core portion of the quantum dot. Fluorescence correlation spectroscopy, from using this from time measurement, we cannot get the dynamic radius or high dynamic size, because core will only give this semiconductor portion, the size of the semiconductor portion, not the capping layer. But if you want to know the entire size, including the capping layer, he should study this fluorescence correlation spectroscopy. So fluorescence correlation spectroscopy is a single method, and from this curve, after treating, we can get the diffuse translational diffusion time of the molecule. And now using Stokes equation, we can from the diffusion constant. So this will tell you the diffusion constant, and from there we can get the size of the molecule. And here we get the size of the molecule, and we found also the length of the capping agent from here, and we found that capping agent, the hydrodynamic length 6 nanometer. We found the hydrodynamics means the entire molecule, but in this semiconductor portion, often from the time measurement is around 5 nanometers. So the length of this one is capping agent is around 1 nanometer. So I also calculated the rate efficiency using lifetime state measurement, and we found a different quencher concentration, acceptor concentration, and we found that there is a nice matching between the steady state and time reserve. This is indicating that in the lifetime measurement, we almost detected 100% rate. So dependence, temperature dependence also, if we increase the temperature, we found that the emission peak position of the quantum dot, that is donor, is shifted to the red side. And now it's shifted to the red side, so this is at different temperature. It's showing basically the emission spectrum of quantum dot, and you found, and this is the absorption spectrum of quantum dot, and you will find that the extent of overlapping between donor emission within the current, that it's from 400 by 20 nanometer. So it was published in chemistry. I already finished my to present this. So very important. So recently you will find there is a surge in carbon dot field. The papers are publishing. So I found one up to 2006, there's an exponentially increases number of papers published per year. But there is some problem with carbon dot field, because most of the author did not purify the sample with more scientific way that causes some apparently interesting observation, but later we found that is all due to that. So I found that it's not that fixed. There's an exponential number of because carbon is on top of water, stable, highly fluorescent, and this is a carbon allotropy, and people have interest on carbons. Obviously, this is well accepted community. The second point is one can easily synthesize this one using facile one-pot synthesis method, and the most interesting property of this carbon dot is excitation dependent emission. So you can generate any emission wavelength at your choice by changing the excitation wavelength, and it has a very good application in LED or other photovoltaic devices. Now we've found that this studying several literature, this carbon dot has a broadly it has two different portions. One is core carbon. Core carbon is formed by basically.
Sir, can you hear me?
Yes, I can hear you.
Yeah. Sorry for the interruption, sir. Actually, we are running behind schedule, and I'm very sorry for that. And yeah. So you have to finish it by 2 minutes, sir. 2 minutes.
Okay, sure.
Please don't mind, sir.
Okay. So it has like one carbon input, and other surfaces it contains some caffeine, and synthesis I'm having the types I can skip it. So we size this carbon dot, and we basically through silica column separation we could able to separate this carbon dot into two batches. And also this is the tab image, and this is briefly showing you the separation method. And after the spectroscopic studies, and we found there is no in the crude carbon dot sample there is excitation dependent emission, but after careful separation of carbon dot to different batches, we found there is not at all any excitation dependent emission properties. So now I'm going to conclude. So excitation dependent emission of fluorescence carbon dot arises due to the ground state heterogeneity and several striking phenomena of fluorescence carbon dot, like excitation dependent emission, highly fluorescence, and breakdown of Casas rule. Everything reported in high impact journal is basically due to the impurity in carbon dot. I would like to thank everyone for my talk. So any question from the audience? Am I audible now?
Yes, sir, you are audible.
Okay. So yeah.
Unfortunately, sir, your network seems to be a little poor. Your voice was continuously breaking during your talk. Very unfortunate. Actually, we couldn't do anything about that. We can't do anything about network, right?
Exactly. This is not in our control.
Yes. Okay. I mean, as we are running behind the schedule, I'll request the audience to contact Dr. Ghosh.
Okay.
If they have any query through his personal email, because we have to carry on. But let's please thank Dr. Ghosh for his keynote, such a wonderful keynote address. Now we will continue. Sir, can you just switch off your presentation mode?
Yes, sure.
Yeah. Yes, sir. So yeah. So our to the talk. So our next talk. So now this talk will be about the talk or discussion on the topic. And our next talk will be given by Dr. Ravikiran Saripalli. He's a friend of mine, and he's currently a postdoctoral fellow in the Department of Quantum Information and Nonlinear Optics in Tulane University in USA. He has been in